Hello and welcome. Today we're going to dive into the secret science behind some of the most common things you use every single day. We're talking about the magic that happens when you wash your hands, do a load of laundry, or even just mix up some salad dressing. We're talking about surfactants. These are the unsung heroes of our daily lives, and we're about to find out exactly how they work their magic.
So let's start with a really simple question that you've probably run into 1,000 times. You know the feeling. You've got greasy hands, maybe from cooking or working on your car. You stick them under the faucet and what happens? Pretty much nothing, right? The water just beads up and rolls right off, leaving all that grease behind. So why is that?
Well, the main culprit here is something called surface tension. You can think of it like this invisible, super thin skin on the surface of water, and it's all because water molecules are incredibly attracted to each other. They're like a tight-knit little group. They would much rather cling together than spread out and mix with something else, especially something like oil. And that resistance, that refusal to spread out, is really at the heart of a classic conflict, one that plays out in your kitchen sink every single day. It's the age-old problem of oil and water. At the molecular level, these two just do not get along.
The reason they don't mix all comes down to their basic structure. You see, water molecules are what we call polar. This means they have a slight positive charge on one end and a negative charge on the other, kind of like tiny little magnets. Oil molecules, on the other hand, are nonpolar, meaning they have no charge at all. And because of that huge difference, there's just no attraction, no way for them to bond. They pretty much just ignore each other.
So, if oil and water are basically natural enemies, how do we ever get them to cooperate? Well, we need a mediator, right? We need a hero to come in and bridge that gap. And that hero is the surfactant molecule. It's kind of like a chemical peacemaker with a very, very useful split personality. The name surfactant is actually a big clue. It's short for surface active agent, and its whole job is to get right in there, right at the boundary between two things that don't mix, like our oil and water, and latch on. The technical term is adsorb, and by doing that, it just drastically lowers the tension at that interface, making it way easier for them to coexist.
So how does it do this? This is where that split personality we mentioned really comes into play. The structure is called amphipathic, which is just a fancy way of saying it has two different sides. On one hand, you've got the hydrophilic head. Hydrophilic, water-loving. It's polar and it's totally attracted to water. But then you have the hydrophobic tail. Hydrophobic, water-hating. It's nonpolar, wants nothing to do with water, but it gets along great with oil and grease. It literally has a foot in both worlds.
Okay, so with this really unique two-sided structure, our hero molecule has two main strategies for bringing oil and water together. Let's break down how it actually gets the job done.
The first strategy is actually pretty simple, but it's super effective. The moment you add soap to greasy water, those surfactant molecules rush to the interface, that boundary between the oil and the water. Their water-loving heads point right into the water, and their oil-loving tails dive into the oil. By lining up like this, they act like a bridge, and that's what breaks down that surface tension we talked about, letting the oil and water get a whole lot closer.
But at a certain point, that interface gets completely crowded. There's just no more room for surfactant molecules to line up. And once you add enough surfactant to hit what scientists call the critical micelle concentration, or CMC for short, that's when they switch to their second, even more powerful strategy.
So think of it like this. Below that critical point, the individual molecules are just floating around. But once you hit the CMC, something really cool happens. Since there's no more room at the surface, they start to team up and build these tiny little spheres called micelles. The water-hating tails all point inwards, creating this perfect little oily core, while the water-loving heads form the outer shell. They basically build a microscopic cage that's perfectly designed to trap grease. And once a little droplet of grease gets trapped inside that oily core, the micelle's water-loving exterior allows the whole package to just be carried away by the water. It's like a tiny taxi service for grease, picking it up and washing it right down the drain. It's brilliant.
All right, now that we've got the science down, let's connect it to the real world. Because these two strategies, breaking down surface tension and forming those little micelle taxis, gives surfactants some serious superpowers that, trust me, you use every single day.
And this process powers so many things. I mean, the most obvious one is detergency, right? Lifting all that gunk off our clothes and our dishes. But it's also responsible for emulsification. That's what forces oil and water to actually stay mixed in something like a salad dressing. It's also behind wetting, which helps water spread out instead of beating up. And of course, foaming. It's what creates that satisfying lather in your shampoo and soap.
But here's the thing you have to know. Not all surfactants are created equal.
Just like you probably wouldn't use shampoo to wash your dishes, scientists have designed all different types of surfactants for very specific jobs. Our hero has many, many different faces.
These different jobs are handled by 4 main families, and they're all categorized by the electrical charge of their water-loving head. And what's really striking is that one type, the anionics, which have a negative charge, just completely dominate the market. At almost 60%, they are the absolute workhorses of the cleaning world.
So each charge type really has its own specialty. Those powerful anionics with their negative charge, perfect for laundry detergents. Then you've got cationics with a positive charge. They're the key ingredient in fabric softeners. Non-ionics have no charge at all, which makes them great for things like dish soap. And then there are zwitterionics, which can have both charges, making them gentle enough for shampoos and skincare products.
So, for example, why are cationics so perfect for fabric softeners? Well, it really just comes down to a simple case of opposites attract. You see, most fabrics get a negative charge when they're wet, so the positively charged head of a cationic surfactant sticks to them like glue. This leaves the oily tail pointing out, which creates this incredibly soft, smooth layer that cuts down on static and makes your clothes feel all fluffy.
So there you have it. From these microscopic taxis for grease to these tiny molecular coatings for our clothes, surfactants are the ultimate mediators. They are absolutely fundamental to how we clean, how we eat, and how we live. And it really makes you wonder, what's next? As we design even smarter molecules, could these tiny heroes help us deliver medicine to specific parts of the body? Or maybe even help clean up massive oil spills in the ocean? The possibilities, well, they're just beginning to mix.